Thank you everyone for attending the defense of my PhD dissertation, which is entitled Deep Learning Approaches for Music Processing in a Computational Musicology Context. It has been supervised by Professors Xavier Serra and Martín Rocamora, and I would like to start by expressing my deepest gratitude to the reviewers and members of the tribunal today. Professor Preeti Rao from IIT Bombay, who is online. We have also Professor Gael Richard from Telecom Paris and Dr. Dmitry Bogdanov. Thank you very much for taking the time to go through our work and attend the defense today. So, computational musicology, it's a very interdisciplinary field, and the idea is to insert computational approaches to process large collections of data with respect to musical knowledge and musical concepts. And, that really enables researchers, on one hand, to corroborate musical hypotheses, and on the other hand, to reveal underlying patterns and structures in data that would be very difficult to figure out otherwise, right? And I would like to take just a second to clarify that the research that we do in this thesis has always the goal of assisting computational musicology research in mind. However, the scope of our research and findings lies on developing music processing tools using novel methodologies, and therefore I would like to say that no pure musicological findings or conclusions will be derived from this thesis. So the topic of computational musicology can be as vast as the world of music itself, and therefore we need to narrow down the scope a little bit in order to carry on with our research. And we choose to work on Carnatic music, which together with Hindustani music, they are the two main traditions, art traditions from India, in particular Carnatic music originated in South India, neighboring regions. It's of course practiced and enjoyed by millions, and it has had an important rise of interest in the field of music information retrieval, opening up a lot of new challenges and opportunities. And also more importantly, Carnatic music was one of the most studied repertoires during the ComMusic project here at the MTG, which also involves other institutions like the one that Professor Preeti Rao leads. And we can build on top of this valuable research resource that happened a few years ago and what happened next. So I would just like to introduce some aspects about Carnatic music that are going to be relevant to this thesis. First of all, Carnatic music
Genís,
is mostly...
Sorry to interrupt you, but you're not sharing the screen anymore on Zoom.
Oh.
Would you mind just doing it again?
Yeah.
Thank you.
Sorry about that. Let me just share the entire screen. There you go. Could you please confirm that you can
That's perfect.
see?
If you want to go full screen mode, it's on the right-hand side. Perfect.
Cool,
Awesome.
thank you. So, Carnatic music is mostly joined live because it is highly improvisational, and therefore interaction between artists and at stage is crucial, and also is generally distributed via audio recordings, and therefore we're going to base all our research on top of processing audio directly. And although many different performance formats exist, the most common format nowadays is led by a singer that is accompanied by a violin that creates an heterophonic texture with the singer, interleaving and shadowing its melody. Usually, we have a pitch percussion section, normally led by the mridangam, which is a double-edged drum that is in tune with the other instruments. And what gives this tune is the tempora, which basically plays the tonic. It's a consistent frequency value that lasts during the entire performance that gives the foundation for all the instruments to be on tune. So I think it's going to be better if we just listen to 30 seconds of this amazing performance by Dr. Brinda Monica Basakan last year.
Kadaikan vaitennai alam
Cool. Let me just go back to the presentation. There you go. So for Carnatic music, but also for all the repertoires out there, many musicological questions depend on fine-grained, time-aligned descriptors that are normally now distributed together with audio. And therefore we need to process raw audio before actually performing the actual musicological research. And here you can see some examples of some of these processes that we can perform on top of audio for feeding what is the musicological relevant research. However, manually performing all of these processes at scale is generally not feasible, and therefore we need to rely on music processing tools to perform that, right? Because music processing involves automated routines to clean, analyze, and extract information from raw music signals. And for many decades, algorithms that operated on top of audio handcrafted features and that leveraged musical signal processing and statistical knowledge were used to basically perform this information extraction from audio, right? However, these handcrafted bottlenecks usually hinder proper scaling up and generalization of these algorithms to large collections of real-world audio and also noisy contexts. And here is where deep learning comes into play, since deep learning is a technique within artificial intelligence in which we have large networks of parameters that can process, in this case, raw audio directly, learning, features from the audio and complex patterns in order to solve a given number of tasks. No? And one other nice thing is that deep learning models can actually scale to arbitrarily large data sets, and last but not least, they show a state-of-the-art performance for several downstream tasks when we have the data available. No? And that's why deep learning is now the preferred solution for several music processing problems. However, deep learning also is not free from challenges, and one of the challenges that deep learning models can over-specialize, which means that when we train a model on a given domain, or in other words, on a given music repertoire, in this case we're going to use domain and repertoire interchangeably. So imagine we train a model or optimize a model for a given task on blues data, then if we apply it to Carnatic music, we usually see a performance degradation, which is actually happens because we have this problem that is named domain shift. And basically happens because when we change repertoire, we change a lot of aspects of the music that affects, we change performance practices, we change instrumentation, we change singing and performance techniques, and a lot of information that change the particularities of the signal, and that affects that the model cannot really leverage the complex patterns that learned from the previous repertoire. And we're going to be studying this problem for some interesting and relevant tasks for the analysis of Carnatic music. And we're going to narrow down the scope a little bit more, because otherwise, again, it would be not feasible to do our research in a timely manner, right? So we're going to first focus on the melodic analysis of Carnatic music, although analyzing other dimensions of music like rhythm and structure is also super relevant. Melodic analysis yields a lot of interest and challenges in the community. We will focus on the singing voice, which is the main source in the most common performance arrangement. And then we're going to focus on these two tasks that I'm going to quickly introduce. So first we focus on vocal melody estimation, which is the task of automatically predicting the melody performed by the lead singer. And in the context of Carnatic music, we preferably annotate it in time series or contours of pitch or fundamental frequency values, because ornamentation and details on Carnatic and also on Hindustani music are crucial to characterize the melodic framework, and therefore it's super important to be able to characterize this fine-grained detail. And then we also work on singing voice extraction, which basically is the task of predicting the isolated vocal stem from a given music mixture. So we have the audio of a performance, and we want to get the audio of the singing voice alone. And, vocal melody estimation in the context of Carnatic music is normally addressed using signal processing-based methods, which for other domains have been already outperformed using the latestly published deep learning models, while singing voice extraction is addressed using deep learning models that have been trained using repertoires from other domains, creating this potential performance degradation given the domain mismatch. And this is basically the data that we would ideally need to train these models directly using in a supervised fashion. For vocal melody estimation, we would need mixtures annotated with frame-level vocal pitch annotations, while for singing voice separation, we would need corresponding groups of mixture with the corresponding solo vocal stem with the corresponding isolated accompaniment audio stem. And for Carnatic music, while no mixtures annotated with these annotations are available, since it's a repertoire that is mostly performed live, it's rarely recorded stem by stem, and therefore it's really difficult to find and also to compile completely isolated multi-stem data. Let us see, however, what we have in the literature. So interestingly, we find in the literature open and large collections of multi-stem recordings from live performances. And that means that we can just record directly the microphones from live performances through the mixing controller, which again, it's easier and faster to collect. And it has ecological validity, and these recordings are going to be really relevant from a musicological point of view because they are recorded in a real world scenario, right? However, as you can see in this picture, the contiguous microphones are pretty close between each other, and that produces a problem that is called source bleeding or source leakage, which basically happens when this microphone is going to basically pick up sounds from the contiguous sources, and also the room acoustics, noises from the audience, and so on and so forth. And interestingly, we have a large data set that has more than 60 performances recorded in this format, of course with the permission of the artists and the venue, and it's called the Saraga dataset, and it's a really, really interesting resource. And I would like to basically play you how a signal, how a vocal source, the signal from a microphone from the singing voice sounds in Saraga. So I guess that you could hear that although the singing voice is predominant in its corresponding microphone, the rest of the instruments are pretty audible in the background. And Krishnan and colleagues in this paper from 2024, they provided a very beautiful mathematical proof that if you use this data to train directly deep learning models in a supervised fashion, you cannot expect the models to perform on line with the state of the art, right? And however, we are very interested on seeing how we can exploit these recordings, to leverage the domain knowledge or the domain information in these recordings, given its value, and be able to train deep learning models with that, right? So from a methodological point of view, the research objective of this thesis is to basically see how we can exploit these recordings in order to train deep learning models that are in domain with the Carnatic case. And then from a more practical point of view, we want to see if the models that we adapted can actually have a positive impact on subsequent research. Right, so this is going to be the line of this presentation. It is in a slightly different order than the thesis manuscript, but I wanted to start from the more dense topics and then finish with the lighter ones. At the beginning of each chapter, I'm going to show two boxes, one stating the problem that we want to address, and one showing the actual idea that we implemented. And let's start talking about the vocal melody estimation part. So the problem here is that while the vocal melody estimation literature is pushing the performance up using deep learning models in the context of Carnatic music, most of the work on computational analysis of Carnatic music relies on methods previous to that, given the lack of training data. Therefore, our proposed approach is basically to artificially compile large amounts of training data for Carnatic vocal melody estimation, train a deep learning model with that, and then basically see if the performance can actually improve the previous approaches. So the work in this chapter corresponds to this TISMIR journal paper that it was published a few years ago. And although in the context of the work in this chapter, I also contributed to these two papers led by my colleague Thomas Nuttall, I'm not gonna actually cover this in detail. So this is a literature review we perform on computational analysis of Carnatic and Hindustani music. We review papers related to this topic as much as we can, finding out that it is not properly seen, but almost 90% of these papers rely on these time-aligned melody annotations. And even if we review how many of the papers operating on deep learning still rely on these annotations, it's about the 63%, which actually points out the relevance of these type of annotations for Carnatic music. And the topic of vocal melody estimation have been addressed using many different points of view. I think that one way of grouping them is salience-based methods, in which Professor Priti Rao had a strong contribution to, modeling-based methods or approaches, in which, again, Professor Risher is also strongly involved in these papers. And then we have the deep learning models, which, if we have the ideal data to train, they perform really, really well, right? And unfortunately, in the interest of time, I won't go into detail of how every approach here works, but I just want to highlight that the salience-based methods are the approaches that have been mostly used in the context of Carnatic music. Therefore, we take a look at those in particular, and in particular Melodia, which was developed by Salamon and Gomez here at the MTG. We have a very efficient and beautiful implementation through Essentia, which is a software developed by Dr. Dmitry Bogdanov and maintained by him as well, and we're going to rely on this approach as our baseline for these reasons. So again, the idea is now to basically compile data to train deep learning models for vocal melody estimation for Carnatic music. I'm going to walk you through how we are going to do that. So we're going to take multi-stem performances from Carnatic music in the Saraga dataset, and we've seen that we have this source bleeding, so we need to clean it up as much as we can. We're going to rely on two-stem splitter, which is a deep learning model for vocal against accompaniment source separation. It's pip installable, really efficient and easy to use, and we will see in a few slides later that it has been broadly used in the context of Carnatic music, because although it is out of domain, it has been trained with a lot of different vocal data, and therefore we expect that it has the potential to keep the quality of the vocals pretty well. And then we just perform like some cleaning of the voice regions using an energy filter. Once we have this clean singing voice, we're going to perform a preliminary prediction of the corresponding melody by using predominant melody MACAM, which is an adaptation of Melodia that prioritizes longer sequences. And we expect that that will help us on characterizing these, intricate ornamentations in Carnatic music, which are super important to have in our data set, right? If you want to train a deep learning model with that. And once we have this pitch track, we will basically process it using a repertoire-informed pipeline from previous work. We're going to basically smooth it out for a better analysis, but taking care that we do not smooth out the characteristic ornamentations. We're going to fill out the gaps that are shorter than expected. And then what we're going to do is basically we're going to take the vocal signal that we cleaned up, and we're going to, using the harmonic plus residual model, we have a nice implementation for that here at the MTG. We're going to use this model to split the harmonic plus the stochastic part, and then we're going to recompute the harmonic part using the known pitch track, right? And then we're going to take this recomputed harmonic part mixed with the original stochastic to get a singing voice that, of course, is resynthesized by an algorithm that estimates its components, so it potentially has artifacts, but it closely follows the harmonic structure of the singing voice. Is going to closely follow the melody that we have at hand, and therefore the singing voice is going to be perfectly annotated. And now the idea is to basically remix these vocals with the rest of stems using musical informed weight so that the singing voice stays predominant, but trying to add some augmentation as well. And then, since we don't have tempura stems in Saraga, which are super important, we took this model from von Wallstein et al., which was in MATLAB, and we actually adapted it so that we can output arbitrarily lengthy audios, which was not possible, and it was also not possible to input arbitrary pitch for the tonics, and we also adapted to be able to do that. The output of this pipeline is the Saraga Carnatic Melody Sim dataset. It's one of the biggest in the literature for this problem. And we predefine the splitting, the train and test steps so that we don't have overlapping artists, and we store the annotations following the convention in the literature. Right, so now we want to train a deep learning model with that. So we choose to work on the FTANet because the FTANet is a deep learning network that processes frequency and periodicity using attention. And we are interested on leveraging both harmony but also temporal patterns for melody, because that can help disentangling the overlappment between vocals and violin, right? And for that reason, we also prefer this network because also it has like this activity detection branch that is gonna also help us with better voicing detection. So we're gonna start by a cross-cultural evaluation of FTANet by training one FTANet using our Carnatic synthesized dataset, and another FTANet using MedleyDB, which is a melody estimation dataset that, if you let me say like this, we have a Western modern data like pop and rock and related styles, right? However, we process the vocal stems on MedleyDB using our analysis synthesis pipeline in order to reduce the bias towards the synthesis artifacts of our pipeline. And we're going to use the metrics proposed by Bittner and Bosch in order to study voicing recall and false alarm. pitch and chroma accuracy, in this case ignoring octave errors, and overall accuracy. And for the testing set of our Carnatic dataset, we observe a clear gap in terms of the repertoire mismatch, while when evaluating these two datasets on real audio for Western modern datasets, we observe at the first place a general performance drop, which of course might be given the unavoidable synthesis artifacts in our data, but also we observe that the Carnatic FTNet is able to perform decently on these datasets, suggesting that we are not overfitting only to the synthesis artifacts and that we can generalize to real audio. But to keep trying to test this hypothesis, we're going to basically do further experiments. First, we compare the Carnatic FTNet against Melodia, which was the baseline, in which we basically observed that we improve overall the metrics. But I would like to discuss two things from this experiment. First, the fact that Melodia performs within its expected range of performance could mean that, could suggest against a dramatic signal naturalness loss in our dataset, because Melodia is an algorithm handcrafted for real audio, and therefore if our dataset was plenty of synthesis artifacts, we would expect that it fails. And second, one could argue that this experiment is biased because our dataset is trained, our model is trained with the synthesis dataset and is tested also with the synthesis dataset. So we perform an additional experiment in which we compare the Carnatic FTNet with a deep learning model from this paper by Saxena and colleagues, in which they annotated a dataset for Hindustani, Alankar, and Raga dataset. And we should assume that the Carnatic model should be able to generalize better to Hindustani music than on pop and rock, let's say, because Carnatic and Hindustani music share concepts and practices. And we observed that our dataset against a model fine-tuned to this dataset only shows a performance drop of 2.42 points of performance overall, so which suggests that our model, or the model that we train, is able to generalize properly to audio and also to a repertoire that has related aspects. And last but not least, we basically take a melodic pattern discovery algorithm, trying to see if the pitch tracks that we extracted actually can have an impact on subsequent musicological research. And we basically take this algorithm that basically processes an entire performance of real audio that is fully annotated with characteristic melodic patterns by an expert musicologist, observing that when we switch from Melodia to FTNet pitch tracks, the coverage and the precision, recall and F1 score on detected patterns improves on all of the cases, which also reinforces the idea that the pitch tracks that we extract can provide a positive impact on subsequent musicological research, right? These are two examples of characteristic patterns that were detected by the pitch track by FTNet, but couldn't be detected because of Melodia. Melodia, it's this pitch track that suffers from these octave errors, mostly given, the overlap between vocal and violin, right? And you can see that the FTNet Carnatic was able to, output pretty nice pitch tracks in this case. However, you might have seen that during the data compilation pipeline, we rely on Splitter, which actually is a model that actually suffers from the problem that I was actually introducing in the intro. So at this point, since we started working on this topic, we relied on a Splitter, since again, it's trained with, even though it's not trained with Carnatic music, it's trained with vocals that probably will have very different, effects and so on, and that can help, keeping the vocal quality nicely. Also, as we will see in a few slides in the future, a Splitter is broadly used in the analysis of Carnatic music. However, when we informally listen to how a Splitter performs on vocal samples with bleeding, there is still room for improvement. Therefore, that shows that that showed us that the domain mismatch in this topic is clear, and that we need some further research on that topic, which basically motivated the research on the next chapters. Okay, so let's just start by talking about the first experiments that we perform on singing voice extraction from Carnatic music mixtures. So again, the problem that we try to address is that the literature on Carnatic music analysis generally relies on separation systems that are trained on out-of-domain datasets, making possible this performance drop, while the idea is to basically design a strategy so that we can train a singing voice extraction system using Carnatic data, therefore trying to alleviate this domain mismatch, finding a strategy to solve the issue of bleeding, right? And the work in this chapter is basically based on these two peer-reviewed publications that were accepted into contiguous editions of the Izmir conference. So the task of music source separation and music extraction is now also led by deep learning models that can operate on the time, on the spectral domain, or on a combination of both. And however, the leading systems basically predict time frequency masks that then are multiplied by the time frequency representation of the input mixture in order to get a predefined set of sources. And the issue is that compiling data to train a separation models is really complicated and expensive, and that hinders generalization, right? Because we're making networks larger, but the data sets are really difficult to make them bigger. And that's why there have been a lot of research on tackling this problem from an unsupervised or a weakly supervised point of view. Also, Professor Gael Risser had very interesting contributions on this topic. However, in this chapter, we're going to try to tackle this problem from a different point of view. We're going to try to perform bleeding-aware separation, since we believe that that could enable better collection of data from live performances, and it could extend to styles where, music is normally not recorded stem by stem. Again, this is the literature review I showed you earlier. So we took at the papers from 2020 on, when it was when there was this boom on deep learning models that you could access them really easily for everyone. Splitter came out, it was pip installable, it was pretty easy to use, and we saw that at least half of the papers, more or less, rely on source separation models for melodic analysis of Carnatic and Hindustani music, and almost 40% rely on Splitter. So I think now it's a good moment to introduce the Sanida dataset, which was developed at Georgia Tech, not here, and it's a dataset that was published in 2024. It includes 5 concerts that actually were recorded in a way that they could record clean multi-stem data. So it features 5 concerts, so it's relatively small, and it came out kind of at the end of this PhD, and the idea is that they perform experiments on trying to fine-tune Saraga, or fine-tune networks trained on Western music and also networks trained on Saraga, and they didn't observe notable improvement, probably given by the fact that the directly generalizing with domain adaptation is complex, and also given its size. So we will consider that our research is still relevant while using Sanida as a testing dataset to get a nice overview of how our models perform. So the idea of this chapter is to basically perform separation in a multi-step fashion. So instead of basically training models that in one step, in one model run, separate from mixture to accompaniment, mixture to singing voice, we want to go in several steps from mixture to singing voice by gradually removing accompaniment and maintaining the energy of the singing voice. And this is inspired by the theory of generative diffusion models, which I'm going to talk a little bit more about that later. But the idea is as simple as that. And we're going to basically start by testing how this idea works on a controlled environment, on the time domain, using clean pop and rock data and a small network. And then if that works, we're going to basically extend it to give it the bleeding awareness that we want for Carnatic music, right? And basically to perform this experiment, we're going to rely on a wavenet by Retosh et al., which basically is in charge of predicting the next gradual extraction step, knowing at which step of the transformation we are at any moment by basically injecting this information, right? So wavenet, it has been previously used to separate vocals. It's very lightweight, so it enables us to run these subsequent running steps, and then we remove this autoregressive aspect of it. And then basically the idea is to inject this time step in order to inform the model at which step of the transformation we are at any moment. So we perform, again, a controlled experiment using MuseDB with that. And we're going to base our experiments on the standard separation metrics, SDR, SIR, and SAR, basically evaluating overall performance, interference removal, and quality of the singing voice. Observing that when we are using more steps. So when we use 8 and then 20 steps to perform the separation, we are improving quite nicely on interference removal, while also refining the quality of the singing voice, which basically suggests that if we do the separation problem on a more gently pace, we can actually obtain an improvement on performance and refinement on separation, right? Also, as a quick perceptual experiment, we observe that we can take a very small model and boost its performance using this strategy, which is also interesting. But the important thing is that we observe that we can basically condition a separation model to perform this gradual separation idea, right? And now the thing is that we are going to basically extend it to give this bleeding awareness, and we're going to first port it to the time frequency domain, and we're going to port it to Saraga. So the idea now is going to be in T steps to convert from a mixture, the magnitude spectrogram of a mixture, to the magnitude spectrogram of the singing voice with bleeding. And now instead of having a wavenet that basically predicts the next step given the step T and the previous step, or the next state, let's say, now we're going to train a unit that is going to basically predict time frequency masks to go to the next step, given the step that we put in as input. This is the whole approach. Let me just go through it slowly. So once we have this model trained, we're going to perform inference on real audio recordings, and we're going to basically take all the transformation steps and stack them together into a feature matrix. And now what we're going to do is basically observe how each frequency bin evolved through the transformation. And we basically intuitively think that if the transformation goes well, the bins belonging to the singing voice will maintain its energy, while the bins belonging to the accompaniment will be converted from accompaniment down to bleeding, which is not going to be zero, but there's going to be an energy difference, right? And the idea is basically to cluster bins using this information, using k-means clustering, and we could use basically only 2 clusters to build the binary mask. But since we have a strong overlap in music, in Carnatic music in particular, we have this overlap between violin and singing voice that we want to address. And in this case, I think it's important to be able to characterize these bins that will have shared information of overlapping sources, right? And for that, we let the user use more clusters, which will basically encompass all of these shared bins. And then we also let the user choose to be more restrictive with clusters that are close to the accompaniment cluster, to the centroid of the accompaniment cluster, in order to push a little bit more the isolation of the singing voice, of course at the expense of vocal quality, because if we remove more bins that have shared information, we're going to be also removing information of the singing voice, right? And actually, this behavior is shown in this experiment. So the more clusters that we use and the more clusters we remove, the best interference removal we obtain, while at the loss of vocal quality, right? And when we basically compare the performance of this model against the baselines, so we're going to basically take a unit, we're going to train this unit with raw Saraga, and we're going to basically compare it. And we observe that when, using this first multi-step separation and then this masking clustering, we obtain a strong improvement on interference removal, while we have a small loss on perceptual quality of the vocals in this case. However, when we compare with the splitter, while we still observe a nice improvement on interference removal, in terms of vocal quality, in this case, the loss of quality is way more apparent. However, we run a very interesting experiment in which we basically use the separations from our system and from splitter to predict melody. And we observe that our system is able to obtain a slight improvement on melody prediction using a monophonic pitch tracker, which takes into account leakage again. So, which actually suggests that for feature extraction, our separations would provide an improvement. And however, we want to put like perceptual numbers into these metrics. And we run a perceptual test in which we compare a very strict version of our model against a splitter, observing that the gap in vocal quality is smaller than the gap in vocal isolation, in which users really graded our model with a large margin on top of a splitter. And we're gonna listen to a few examples of that now. So we're going to first listen to the mixture, then we're going to listen to the splitter separation, and then ours. Mixture. Splitter. Our method. So let me play another example. Let me play the short one in the mixture. Splitter. Our method. Right. So I think that it was. So I think that these examples exemplify quite nicely what the perceptual results suggest. Now we have like an improvement on source isolation, while a splitter is able to, given the large amount of training data and on different vocal data as well, to preserve the quality of the singing voice better. Also, the nature of our approach affects, the vocal performance. However, I think we would like also to argue that the components of the singing voice that are mostly wiped out by this algorithm do not belong to the core structure of the singing voice. Its harmonics, and the gross envelope and main structure, which also suggests that, on the side of feature extraction, it could help for better pitch extraction. And also, if we would like to analyze vocals alone, from a musicological point of view, these separations could also position for a better analysis. Cool. So let's now move to the generative part of the separation work or the extraction work in this thesis, which I would like to say that probably is the part in this thesis in which we had like a more focus toward general methodological novelty. However, I believe that improvements on this topic can actually have a nice potential positive effect on the separation for Carnatic music as well, starting by the fact that, one of the problems that we want to address or that motivate us to work on generative source separation is that frequency masking separation systems are of course leading, but are inherently limited by this source overlap in music. And in Carnatic music, we've seen that this is super apparent in this previous chapter now, where we've seen this trade-off between quality and interference, that it was quite apparent. And when we started this thesis, although there had been previously attempts to perform a separation from a generative point of view, there were these recently emerged diffusion models that were showing really nice performance for audio generation, and therefore the idea is to basically try to apply these models on this task and see if we can give them some bleeding awareness as well. The work in this chapter corresponds to these three peer-reviewed publications. The first two were done in the context of a research collaboration with Moises AI under the supervision of Igor Pereira. And then when I came back from this internship, we did this last paper that was accepted in last year's Izmir. So here we have the diffusion models, which basically are widely known right now, but basically the idea is that we have samples from a given target distribution that we want to generate, and then we add small amounts of Gaussian noise to the samples of this distribution until converting them into samples of Gaussian noise. And then the idea is to train a model to reverse this process, and we are underlyingly mapping points from an easily tractable distribution to points on a more complex one, right? And the idea is that when we have this model trained, if we input a random sample of Gaussian noise, we will receive a random observation of the distribution that we approximated, right? However, it has been seen that these models offer a nice flexibility to be conditioned with additional information, so that we can basically give additional information to guide the generation process toward the target output that we want in the target distribution, right? And that has been used for audio inverse problems as well. In particular, speech enhancement is a core topic there. And when we started this thesis, singing voice separation using diffusion models was barely explored, and therefore we were interested on exploring how these models work for this task, right? And of course here we need to take into account that the complexity increases given the strong correlation in music, which makes this task harder. Also in the case of Carnatic music, again, we need to put extra attention and try to preserve source identity, maintain the melody of the source, and avoid generative artifacts on complicated, intricate vocal effects and singing techniques, and also given the overlap with other sources. So this is the pipeline that we followed. The idea is to just provide an extensive base of generative experiments for singing voice extraction, in which we sample singing vocals, conditioning on music mixtures, right? And we used B-objective diffusion, which is a slightly different implementation of the diffusion process that provides further stability. We couldn't see it really used in the audio inverse problems literature, and we integrated directly, and actually we believe that it provided nice quick training and so on, and that was really nice. And we begin by training a waveform generation model, in which basically we get inspired by this paper by Joan Serra and colleagues. It's the universe model, and basically it basically performs a speech enhancement. And since it's private, we implemented it from scratch, and we also added some modifications inspired by the separation literature. This is the overall model. It features two unit networks, one that is in charge of processing the mixture towards adding a nice conditioning to get the clean singing voice, and the other one is in charge of converting from Gaussian noise to the target vocals, right? The conditioner model is leveraged from the universe paper, following the indications in the paper. However, we add some diffusion, some separation-inspired improvements in order to enhance context in the time axis, which has been shown to provide improvements on separation models. And then for the unit, we use a different unit than universe that was used before in generative modeling for music, and also features time-wise self-attention, and we believe that it could provide improved results. And one also interesting thing is that the sampling process of this parameterization of the diffusion process is inherently deterministic, which means that if we give the same Gaussian input, we will always end up into the same output. You know, that provides efficiency in performance. That was the nice thing. So for audio inverse problems, it makes sense, but it's also quite rigid. So researchers have been trying to add some stochasticity to this process in order to give some flexibility to the generation trajectories of the models, right? So here we propose to actually leverage the same idea, but only applying it on the high frequency end of the spectrogram, of the signal that is being generated, trying to give the flexibility only in the high frequency end where the data is more difficult to generate in terms of music, and also where the separation models accumulate more errors, both in the time and also in the time frequency domain. So we again use MuseDB, controlled scenario, clean data, non-Carnatic. We basically train our model with MuseDB, observing improvements over the previous early generative models for singing voice separation. And when we use extra data and we use our improvements, we observe a nice performance boost, getting closer to the separation baselines. Although we need to take into account that generative models tend to be extra punished by the phase-dependent metrics, because when we add this generative nature to our approaches, we can have phase mismatches and slight variations that are not perceivable at naked ear, but that affect the actual metrics. And another interesting thing that we observe is that by adding this flexibility on the high frequency end, by adding mild stochasticity above 5K, the network is actually capable of boosting the SDR 2 dBs up, and we actually observe that the samples sound with less noise and sound more natural to our ears. However, generating waveforms is expensive, and also to get the model to shine, we needed extra data, and that is complicated to extrapolate in a computational musicology case, right? We want to get a model that is efficient, and therefore we propose to extend to latent diffusion, which basically, instead of generating waveforms directly, now we're going to leverage an audio neural codec or an audio encoder that is basically going to encode the waveforms into a compressed representation. We're going to basically train the model to generate these representations, and then we're going to basically decode them to be able to listen them. No, and we use encodec, which has an encoder, a quantizer that compresses further, a dequantizer and a decoder, and we basically performed a noise robustness experiment in which we observed that the continuous non-quantized representation of encodec is robust to mild amounts of noise, which actually is pretty relevant, because that means that if we use this representation for diffusion modeling, since we start from Gaussian noise, if we have noise leftovers, we can basically, the model is, the decoder is going to be robust to that. No? So here we do not use conditioner because we want to not make the model grow with, more, and we actually are injecting the mixture already processed by the encoder so that the conditioning model stays in the same domain as the vocal that we want to synthesize or generate, and therefore we expect that the feature learned by the autoencoder itself will help us with further learning. So here I would like to say that we discard SDR completely because here we included this latent framework that exacerbates a lot the phase mismatch, and therefore SDR or phase dependent metrics are not really are artificially boosted down a lot for generative models using this latent framework. Therefore we rely on a spectral quality metrics, observing again improvement against the previously proposed models for that, and getting closer to the actual deterministic baselines, and also on log pitch error, which is computed using a monophonic pitch tracker as well. We obtain a performance against the previously proposed models and getting closer and closer to the deterministic ones, which is also super interesting. And again, this is done also on MuseDB, controlled, non-Carnatic, clean, and a proof of concept. And then since we don't have SDR, we run perceptual tests on 20 listeners to basically try to give numbers to important aspects on separation, observing that our model is able to get practically the same results as bandsplit RNN, which is one of the best baselines. And however, in terms of intelligibility, there is still room for improvement, probably given the fact that in the context of singing voice separation, generative artifacts get accumulated with the codec artifacts, and on difficult cases where we have a lot of overlap or weird effects of the singing voice, this has this hinders proper generation and creates this slight intelligibility downgrade. And in terms of efficiency, you can see that the inference time is reduced a lot using the latent framework against previous approaches, and we are pretty close to hybrid demux, which basically is a model that is run in a single step, while ours is run on 50 steps, right, to perform the diffusion process. Cool. So now we come back from Moises, and we try to leverage on these findings to give some bleeding awareness to the model. So first, we want to keep improving on efficiency to keep getting closer to a more musicology scenario, and we basically substitute encodec by music to latent, which was a recently published neural encoder that compressed the data quite a lot more, and also we were interested on exploring how it worked for diffusion. And to perform the bleeding awareness, we're going to be inspired by classifier guidance, which is basically a technique in which when we are generating a sample using a diffusion model, we're going to leverage an external classifier to basically predict the class. In this case, we are talking about image generation, by the way. We're going to try to predict in which class this sample belongs to, and then we're going to compute the gradient with respect to the target class, and use these gradients to push the trajectory of the sample towards the sample that we want to generate. And that was shown to provide nice improvements on image quality, no? So the idea is to leverage this idea on our case. So we take the latent diffusion model for separation, we train it conditioning on mixtures and separating vocals with bleeding in Saraga. So the best that the model can do is generating vocals with bleeding. And then we're going to leverage an external bleeding predictor, which is a network that, given a vocal signal with bleeding, it tells us from 0 to 1 the ratio of bleeding that we have in the signal. And then basically we're going to compute the gradient with respect to 0 bleeding and use that to push the generation trajectory toward areas in the manifold that the network has learned to seek for samples with less bleeding, right? And this idea of the bleeding predictor was leveraged from this paper that was accepted at the WIMAGA workshop in ICASP, in which we used this idea of the bleeding predictor to fine-tune a deterministic model for Carnatic source separation, in which we basically better disentangle vocals and violin. And this work was led by my colleague Aditi Shankar, and basically we leveraged this idea. We trained this network using MuseDB, creating artificial bleeding samples and training the model with that. And basically, This big table is like an evaluation study together with all the results. I just want to summarize it by saying that we compare different guided versions or bleeding guided versions of our latent diffusion model against the previous networks that we proposed in this thesis, observing that when we mildly push the trajectory with this technique, we have improvements on most of the spectral quality metrics and also on pitch detection as well. However, when we do a preference test on comparing how our samples from this model compare to the previous models on this thesis, we observe that while there is a strong improvement on interference, in terms of quality, this model is not preferred by most of the participants, which suggests that there is a room for improvement on source quality and artifacts, which might be given on one side by the fact that we are relying on some components that are out of domain. Music to latent hasn't been trained for Carnatic music, while the bleeding predictor is trained for MuseDV. And while the code for fine-tuning music to latent was not available, the bleeding predictor could have been trained with Sanida, but we wanted to keep Sanida as a testing data, and we would not want to bias the results. No? So for, while probably these separations could enable better feature extraction and pitch prediction, we need to also take into account that perceptual quality is important if we want to apply these separations on a more musicologically relevant or in a context where we want to study the singing voice from a musicological point of view, right? Cool. So let me quickly cover some additional contributions that we made within the context of this thesis, but that I think that are super relevant to the work that we've done. So first, distribution of music datasets is of course challenging given many issues, and at the same time we have shortage of frameworks that help researchers on further research and experimentation for the context of Carnatic and Hindustani music analysis. And to address a little bit these problems, we first curate the Saraga dataset and contribute to data openness and dissemination, while we develop open frameworks to support tools and datasets to work on the topics that we covered in this thesis, in particular computational analysis of Carnatic music. And the work in this chapter corresponds to these two papers, or these two papers are related to the things that we did in this chapter. In this paper, we published an extension of the Saraga dataset in which we have more concerts and we have videos as well. However, the main contribution, which was recording the actual data, was done by my colleague Aditi Shankar, and therefore I will let her get into more detail about this work in her presentation in a couple of years. But so when we started this thesis, we had Saraga, and which was a very relevant resource, but we did not have a secure access point to the canonic version of Saraga. So basically we did some work on cleaning up Saraga, securing an access point, and more importantly, creating a Mirdata data loader for Saraga, Carnatic and Hindustani. And Mirdata and Sound Data are Python libraries that are used to download, validate, and then access and use datasets for music and sound. And that is super relevant to enhance reproducibility and so on. And from this contribution to include Saraga there, a very nice collaboration grew up, in which I was doing active maintenance for all these years. I added a lot of new upgrades to these libraries together with the collaborators, including this journal paper of the design principles of sound data. I did a lot of code review, and I also did a few talks on conferences, basically talking about the design principles of these libraries. And also importantly, we developed a framework that is called CompiAM, Computational Models for Analyzing in General Music. And the idea here is that we want a common code framework to enhance reproducibility in this research field that also helps newcomers getting an easy introduction to the topic with access to tools, and also for research dissemination, so that people can also include their tools there. So while no resource like that existed before, we basically implemented it as a pip installable Python library that provides access to dataset loaders via Mirdata loaders, processing tools and algorithms for Carnatic and Hindustani music, visualization functionalities, and also some pre-trained models. So as of now, we have 10 datasets. So CompiAM provides access to 10 datasets. The dataset from this thesis is included. we have access to 12 tools and models for 9 different tasks, from which 7 are pre-trained models that can be directly used. The weights are downloaded automatically, and you can just run easy inference. The models in this thesis are also included there. And we also written and published DMX Diffusion, which is a code base for supporting diffusion-based experiments for audio inverse problems. It's highly modular, so people can integrate their own networks and modules there pretty easily and just reconfigure them via Hydra configuration files. And it's the first implementation of this kind, was done during my internship in Moises, and it basically supported all the experiments in this thesis, and now it's open to reproduce the results of our work and also to enhance further research on this topic. And I would like to start wrapping up this presentation. So we've already talked a little bit about the outcomes and limitations of each of the contributions of this work, but however, I would like to very quickly summarize the actual contributions. So we basically compile and create and publish a large and open Carnatic vocal pitch dataset together with a deep learning model that shows improvement on the vocal melody estimation task, but also quite a nice impact on subsequent musicological problems. We proposed an iterative training strategy that let a small model improve or refine its performance, and that then we extended it so that we could train a singing voice extraction model using in-domain data with bleeding, showing particularly improvements on interference removal. We did a base of generative experiments for singing voice extraction using diffusion models, showing the potential of this approach and perceptual and competitive perceptual quality. Of course, that is, a way to go on this topic, and we proposed a novel methodological idea on, guide the latent diffusion model towards reducing the bleeding in the generations. However, this work has still room for improvement on perceptual quality in particular. And finally, we have done active contributions on open and reliable dataset and model distribution and use, which is also quite important. So talking about, the application or the relevance of this work in a more applied point of view, we've already seen in our own experiments, but also on other papers, that our models are used and, have and are being used at a position, to be used for further musicological analysis, while, all our resources are available online to download, to review, to use, and to, integrate to your research works. And last but not least, we also did some nice research dissemination. I was like a speaker on the Izmir tutorial, in which we basically presented corpus-based approaches for corpus-based research on Indian music in Izmir in Bangalore. It was really nice. We created like a nice webbook for introducing newcomers to the task of computational analysis of Carnatic and Hindustani music. And then I was also organizing and lecturing a workshop in IIT Madras together with a lot of experts and computational musicologists and musicians and so on. It was also a really nice and enriching experience for my career, and also for learning a lot of interesting things about the musical repertoire as well. And then I just want to leave this presentation with some future outlook. So I think that one idea that applies to the 3 main topics of this dissertation is extending the proposed work to other instruments within Carnatic music and to other repertoires. Actually, we just integrated to Compiam a model that basically leverages our vocal melody extraction work for violin. So that's very nice, and the idea is to keep, the ball rolling. We also, the task of vocal extraction and vocal melody estimation are 2 tasks that live quite well together, and now that we have in-domain models for both, could be good to bring them together in order to improve the overall quality. In terms of vocal extraction, we also and especially need to work on improving source quality. And there is an experiment that I think that could be super interesting to do, which is that while generative models using diffusion have shown nice generalization potential, it would be cool to do a comprehensive evaluation of how diffusion models can, with non-Carnatic data, generalize to Carnatic data, see if they generalize better to than deterministic models, and see how that can positively impact the analysis of Carnatic music. And then, of course, when you publish code, you publish libraries, you contribute to libraries, you need to keep an eye on on those things, otherwise things get outdated, they break, and they are not viable to use anymore. All right, so quick shout out to all of the co-authors of my papers. This is a non-exhaustive list, but these people are the people that has more actively worked together in my papers, in particular Dr. Marius Miron, which was mentoring and actually also supervising the very beginning of this thesis. And also wrapping up this presentation by acknowledging in particular my thesis supervisors, Professors Xavier Serra and Martin Rocamora, all my colleagues in the MTG, and also at Moises AI, where I did a really nice internship and where now I joined as a full-time data scientist. Also acknowledging the funding that has enabled this research for all my years. And yeah, saying thanks to everyone, again, as well my family, all my friends for supporting me from another point of view. So thank you very much for your attention, and that was all.